Hello everyone and welcome to this online recorded presentation. I am Ashish here and joining me are my fellow co-authors Kanishka and Deepak. So let's get into the presentation. In this paper, our main focus is radar object detection using super resolution. The title itself provides a clear idea of what we'll be discussing. While the effect shown here may not precisely represent the appearance of low and high resolution radar image, it does give you a sense of what super resolution entails. Let's see what this paper is all about. As you can see from these images, object detection based on vision comes with its unique set of challenges. In the first image, you encounter severe occlusion, making it extremely challenging to accurately count the number of people present in only using the virtual information. In the second image, it's night time, which again means problem. This shows that the effectiveness of vision-based sensors depend heavily on the level of illumination or visibility of the scenario. This leads us to an important question. Suppose you purchase a self-driving car today. Can you trust it if it lacks radar or depth sensors? Okay, uh, I think it's something to ponder about. And then why should you read this paper? This paper proposes the idea of having a standalone radar machine learning system for autonomous driving. This concept is quite exciting because it offers a potential solution for the issues we have encountered in the previous slide, like occlusion or poor visibility. Also, the paper tries to come up with a way without sensor fusion. The sensor fusion is a hectic job because you are trying to make sense of data from all sorts of different sensors. You can get into all sorts of problem, especially in areas like self-driving cars and robotics, all because you have to take data from different sensors. But here is an interesting part which we have used in our paper. If you are if you've already read or about to read a paper, you can see that we use only radar for autonomous driving. You can skip the sweaty part of sensor fusion. Thirdly, our model is a game changer because it's super lightweight and easy on the computing power. That means you can effortlessly put it on any low-cost edge devices without breaking a sweat. This opens up a world of possibility for AI in all kinds of settings, making advanced technology accessible to anyone, even in places where it was previously out of reach. Lastly, if you already have a radar-based object detection system, you can also establish a separate backup radar system that operates independently. It provides you with a redundant mechanism in like some sectors like space and all, where the uh, error is you cannot afford to make an error there. So in those scenarios, a redundant mechanism is very important. So this provides you that redundant mechanism. This backup becomes really useful in crucial situations or when you need to make significant decisions, giving you an additional layer of reliability. Now let's move on to the literature review. In this paper, our concept of object detection draws inspiration from the area of vision-based object detection. Much like in vision-based object detection, we focus on identifying areas of interest that contain specific objects and aim to label these regions. Here we employ a somewhat similar approach by extracting this region of interest for object detection. However, it's really important to note that this presents a distinct challenge because low-level radar images lack the clear geometric boundaries that the cameras provide. Second idea that captured our attention was radar super resolution. This technique is proven to be a valuable tool for mitigating noise and preserving the essential information required for object detection. We'll delve deeper into this concept in the upcoming slide. Lastly, the third idea centered around generating radar data through simulation. Radar data is often not readily available, especially when we tackled radar super resolution. We encountered difficulties in finding a suitable data set containing low and high resolution radar image pair. This is where a concept of simulation came to our rescue. We drew inspiration from a super resolution paper on synthetic aperture radar, which employed simulated data and provided a comprehensive explanation of the process. This inspired us to take matters into our own hand and create our own dataset for radar super resolution. So let's see what we did. Our paper boasts of two primary contributions. Firstly, we created three distinct type of dataset. These include simulated low resolution to high resolution pair of radar maps, and then a pair of low and high resolution data generated from the real world CRUW dataset. And third is the segmented image patches from the CRUW dataset, which are referred to as CRUSEC dataset. I mean, all this data are already available in our GitHub link, which we'll share in the last slide. Secondly, we have introduced an innovative radar object detection technique, which what sets it apart is that it utilizes radar super resolution without the need for any additional sensors. Time series radar data or Doppler domain, we aren't using any of those. We are using only a radar polar data with radius and angular domain, and we're using that for object detection. So that is where our innovation comes into picture. Now let's see how we carried out simulation. So this is a critical part of our work, simulation. We understand simulation isn't real, but how can you say that when there are theories out there which says you yourself are just some 3D projection? That's mind blowing, right? The figure you see here provides an example of simulated high-low resolution pair. The image on the left represents high resolution image, while the one on the right represents the low resolution counterpart. As you can observe in the comparison, there is a significant disparity between a low resolution camera image and a low resolution radar image. Due to the pronounced smearing in the radar image, it becomes challenging to discern the geometrical shapes clearly. In our simulation process, we introduced various types of noise. However, we specifically focused on Gaussian and speckle noise because they most accurately replicate the background noise, and they yielded better results when compared to other available noise distribution during inference. In the table in the right hand side, you will find a comprehensive list of the simulation parameters and their corresponding values used throughout the entire simulation process. I won't delve too deeply into the specifics of these parameters here. For a more detailed understanding, please refer to our paper. Let's move on to our master plan. All right, here is our master plan, somewhat akin to what the professor did in the money heist. As discussed earlier, we begin by simulating both low and high resolution radar images accomplished from the LR-HR heat map generator on the left, that orange colored block. Next, we train a standard lightweight deep learning model it's called DLSR, capable of converting high resolution radar images to capable of converting low resolution radar image to high resolution radar images. Here is where it gets interesting. We employ this DLSR, which we trained on low resolution radar image to get high resolution radar image. We employ this model on real world data, such as the CRUW dataset, to convert the low resolution real world image into the real world high resolution versions. Finally, we have both of these. We have the low resolution as well as the high resolution real world radar map, and we proceed to tackle object detection. So let's go deep into the problem of object detection now. So here is what our secret ingredients looks like. So first, we use the previously mentioned DLSR model to convert low resolution to high resolution radar map, as I covered in previous slide. Next, we utilize that high resolution radar map to extract region of interest from the low resolution map. This process involves two key steps. One is thresholding and other is multiplying the generated mask. Thresholding helps eliminate unnecessary background information. Like you can see that greenish background is there in that CRUW HR image. It helps us to eliminate all this unnecessary irrelevant background information, which prevents us from focusing on the area of our interest. And the mask generation is crucial to capture the spectrum spread of the object in the low resolution map. The inversion step is a very minor detail. It serves to simplify the process. For more in-depth picture, please I recommend refer to our paper to understand it better. It's important to note that both the low resolution and high resolution maps are essential for the successful execution of this process. Low resolution map provides us with a spectrum signature, while the high resolution map doesn't capture that spectrum signature. But the high resolution map aids in filtering out irrelevant background information, allowing us to focus on the areas of interest. From these generated regions of interest, we segment these patches and pass them through an object classifier, which is a standard CNN model. To draw an analogy, it's somewhat like adapting a vision-based object detection architecture to work with radar-based object detection. Okay, here comes the result. Now, You can see in the first image, you will see a car parking lot, an example drawn from a CRUW dataset. As we have discussed earlier, our approach identifies potential area in the low resolution radar map that might contain the object and proceeds to identify them. You can see here the image contains 3 cars here. So from the low resolution map, you can see that there are some dark spots in the high resolution map. So those are the areas which has high probability of containing the object, and we take those areas. We kind of try to run an object classification algorithm on that. We can identify what that patch refers to. Is it a car, or is it pedestrian, or is it a bicycle, or is it nothing? It's just a false false area which doesn't contain any object. Second image here, you can see that there are 3 distinct type of objects: a car, a bicycle, and a pedestrian. It's fascinating to observe how our approach identifies region of interest and classifies them into different categories, demonstrating its capability in object detection and classification. So let's see some results in number format. This table provides a variable comparison of our model's performance in terms of accuracy and parameter count with other state-of-the-art object classifiers. As you can see, our model performs quite well when compared to these other object detection models as indicated in the table. However, what sets it apart is the number of parameters it requires. When you see the other models, they usually have 1.7 million, 2.2 million, or 23 million parameters. But in our case, it's 14.7K only. So it's approximately 100 to 1000 times fewer parameters than the other models. This significant reduction in parameter count gives us a distinct advantage when it comes to deploying this approach on low cost or low power edge-based devices. Our model has an exceptionally low computational footprint, making it suitable for hardware applications. It's worth noting that although we haven't yet implemented it on hardware, we are actively working in that direction to develop it into a practical product. Okay, moving on to conclusion. So here is a summary of the important contributions and limitations of our paper. So we have introduced a brand new framework for radar-based object detection, which sets us apart from existing models that typically rely on sensor fusion or time series data or Doppler domain signatures. Like I said previously, we don't rely on any of that. And then our approach creatively combines simulated and real data to address the challenge of data scarcity in radar-based object detection. This is actually a real problem if there is scarcity of data, and you can handle with simulation, what we did just now in the work. And then one significant advantage of our model is its exceptionally low computational requirement, making it an excellent choice for cost-effective embedded applications. Moving on to the limitations, it's important to note that our model isn't currently an end-to-end trainable network. There is a concern that if we want to pursue this approach, we might compromise its size advantage. However, it's an interesting area to look upon. And then while we are actively working on implementing our model on a hardware platform to make it a practical product, this hasn't been completed yet. This is also a good topic for research. And then radar data presents a unique challenge because it's sparse and highly imbalanced. We have experimented with various loss functions to tackle class imbalance, but we haven't completely resolved this issue. I would request you all to come forward and look into this and like get your own ideas to how to handle this issue. For those interested in accessing our code, datasets, and supplementary materials, you can find them on our GitHub repository through this provided link. And lastly, it ain't much, but it's honest work. Thank you all and goodbye.